The Carrington Event of 1859 set telegraph wires on fire and lit up the sky so brightly that miners in the Rockies woke up at 2 a.m. and made breakfast, thinking it was dawn. If it happened today, $2 trillion in damage, 10 years to recover. Yesterday, we came within one magnetic variable of experiencing exactly that. Earth dodged the bullet not through preparation or warning, but through pure, dumb luck. A storm packing S4 radiation levels and 1,200 km per second winds kissed us instead of punching us, but the sun is far from calm. New sunspots are rotating into view, and oddly, just as the storm peaked, the San Andreas fault line started convulsing. Stay with me to discover why that timing is far stranger than anyone's admitting publicly. Subscribe and follow along, because the next 72 hours might force us to rewrite what we thought we knew about the invisible threads connecting solar fury, our weakening magnetic defenses, and the kind of catastrophic events that leave their fingerprints in ancient ice cores and rock layers. You woke up yesterday morning, scrolled through your phone, checked the weather, maybe grumbled about traffic. Meanwhile, 150 million kilometers away, our star just hurled 1 billion tons of magnetized plasma directly at your face. You had no idea. None of us did, not really. Not until the instruments started screaming. On January 18th, 2025, at approximately 14:30 Universal Time, active region, 4341 erupted. This wasn't some minor hiccup on the solar surface. This was an X1.9 class flare, a designation that sounds technical until you realize the X class represents the most powerful category we have. The energy release was equivalent to billions of nuclear weapons detonating simultaneously. But here's what made this different. What made scientists around the world lean forward in their chairs and reach for their coffee with shaking hands. The flare launched a full halo coronal mass ejection. Full halo means when you look at the sun through our coronagraph instruments, you see an expanding ring of plasma in every direction, a perfect circle growing outward. That geometric signature tells us one thing with absolute certainty. It's coming straight at us. The CME traveled fast, ridiculously fast. Most of these solar bullets cruise through space at 400 to 600 kilometers per second. This one, instruments clocked it approaching and eventually reaching speeds near or exceeding 1,200 kilometers per second. To put that in perspective, you could travel from New York to Los Angeles in 4 seconds at that velocity. When plasma moves that quickly, it compresses the solar wind ahead of it, creating a shock wave that accelerates particles to near relativistic speeds. These particles, mostly protons, began bombarding Earth's magnetic field within hours of the initial eruption. NOAA's Space Weather Prediction Center issued an S4 radiation storm warning. The S scale goes from S1 to S5, measuring the flux of high-energy particles slamming into our magnetosphere. S4 is labeled severe. We haven't seen an S4 event in over 2 decades. The last comparable radiation storm occurred during solar cycle 23, back when most of you were using flip phones, and Facebook was still exclusive to college students. These protons don't care about your atmosphere. They penetrate deep into Earth's magnetic field, particularly near the poles where the field lines funnel them down toward the surface. Within 36 hours, the main body of the CME arrived. The geomagnetic storm that followed earned a G4 classification. G for geomagnetic, 4 for severe. The G scale also runs from 1 to 5, and anything above G3 starts causing real problems. Power grid operators pay attention at G3. At G4, they're on the phone with engineers at 3 in the morning, monitoring voltage fluctuations, watching transformers for signs of stress. Aurora chasers in the northern United States saw curtains of green and red light dancing across the sky, visible as far south as Colorado and Kansas. Beautiful, yes. Also terrifying if you understand what those lights represent. Those auroras are Earth's atmosphere getting hit with so much energy it literally glows. Oxygen atoms get excited by incoming particles, then release that energy as photons when they relax back to their ground state. Green light at lower altitudes, red at higher elevations, where the atmosphere thins. It's physics as art, but it's also a warning sign. Every photon you see is energy that could have gone somewhere else, into a satellite, into a power line, into the delicate electronics that run our increasingly fragile civilization. But here's the thing that kept me awake last night. The detail that transforms this from interesting space weather into something far more unsettling. Despite the speed, despite the S4 rating, despite the G4 classification, our infrastructure held. The power stayed on. Satellites mostly survived. GPS kept working. We got hit by one of the strongest solar events in modern history, and we walked away with barely a scratch. The question isn't why did this storm cause so much chaos? The question is, why didn't it? The answer involves something most people have never heard of, a variable so important and yet so unpredictable that it represents the single largest unknown in space weather forecasting. I'm talking about the interplanetary magnetic field's orientation, specifically a component called BZ. When a CME travels from the Sun to Earth, it carries its own magnetic field, twisted and compressed into a writhing structure called a magnetic cloud. The orientation of that field, particularly whether it points north or south relative to Earth's magnetic field, determines everything. If the field points north, it slides past Earth's magnetosphere like two magnets of the same pole repelling each other. If it points south, the fields couple violently, and all that solar energy pours directly into our magnetic environment. Saturday's CME apparently carried a predominantly northward BZ component during its peak intensity. We got lucky. The cosmic dice rolled in our favor. If that field had been tilted just 30 or 40 degrees in the opposite direction, we wouldn't be having this conversation the same way. Parts of the power grid would have failed. Transformers would have burned out. Satellites would have gone dark. And I wouldn't be calmly explaining what happened. I'd be explaining why your phone stopped working. Now, before you breathe a sigh of relief and move on with your day, I need you to understand something. The sun isn't done. Active region. 4341 is still there, still crackling with magnetic energy. Other active regions are rotating into view. Solar physicists are watching the magnetograms, the images that show the strength and complexity of magnetic fields on the solar surface, and what they're seeing doesn't inspire confidence. The current solar cycle, cycle 25, is approaching its maximum phase. That means more sunspots, more flares, more CMEs. The statistical probability of another major event in the next 72 hours isn't just possible, it's likely. To understand why this matters so profoundly, we need to talk about history. Specifically, September 1st and 2nd, 1859. A British astronomer named Richard Carrington was doing something astronomers did back then, projecting an image of the sun onto a white screen to safely observe sunspots. Suddenly, two brilliant points of light appeared on the sun's surface, so bright they were visible even against the sun's blinding disk. Carrington had just witnessed a solar flare, though he didn't know what to call it. Nobody did. The concept didn't exist yet. 17 and a half hours later, all hell broke loose. Telegraph systems across North America and Europe went haywire. Operators reported sparks leaping from their equipment. Papers caught fire. Some telegraph lines continued working even after their batteries were disconnected, powered entirely by the electrical currents induced in the wires by Earth's violently disturbed magnetic field. Auroras appeared as far south as the Caribbean. People in the Rocky Mountains woke up at 2 in the morning, convinced it was dawn, and started making breakfast. The glow was that intense. The Carrington Event represents the worst-case scenario, the yardstick against which we measure all other solar storms. Modern estimates suggest the CME that caused it was traveling at roughly 2,000 kilometers per second or faster, and the magnetic field orientation was perfectly aligned to dump maximum energy into Earth's magnetosphere. If the Carrington Event happened today, some studies estimate economic damage exceeding $2 trillion in the first year alone, with recovery taking 4 to 10 years in the most affected regions. We're talking about prolonged blackouts affecting hundreds of millions of people, satellite networks destroyed, GPS unavailable for navigation, modern civilization taking a very sudden, very violent step backward. And that brings us full circle to Saturday. We just experienced something that, in raw energy terms, wasn't that far below Carrington levels. The X1.9 flare was significant, though not quite the X45 estimated for Carrington. The CME speed was comparable to mid-range Carrington estimates. The radiation storm was historic, but we survived because of one variable we cannot predict more than 15 or 20 minutes in advance: magnetic field orientation. We rolled the dice and we won. This time, what happens when we roll again? Because we're about to. The sun doesn't care about your mortgage payment or your daughter's soccer game or the fact that you have a meeting on Tuesday. It's a roiling ball of plasma held together by gravity and magnetic forces we still don't fully understand. And right now, it's angry. Over the next 3 days, maybe the next week, we're going to find out if Saturday was a warning or a preview. And there's something else. Something strange that happened while that CME was slamming into Earth's magnetosphere. Something that might be coincidence, or might suggest connections we don't yet comprehend. But that's a story that requires us to look not at the sky, but at the ground beneath our feet. Imagine you're standing behind a shield. The shield is invisible, made of nothing you can touch or see, yet it's the only thing between you and a hurricane of radioactive particles traveling at a significant fraction of light speed. This is your life, every moment of every day. Earth's magnetosphere is that shield, a bubble of magnetic influence extending 60,000 kilometers into space on the sunward side and stretching millions of kilometers in a tail on the night side, sculpted by the solar wind into a teardrop shape. Without it, Earth's atmosphere would have been stripped away billions of years ago, leaving us as dead as Mars. But calling it a shield oversimplifies the reality. The magnetosphere isn't a wall. It's more like a dynamic, constantly fluctuating force field that sometimes protects us brilliantly and sometimes lets in precisely the things we desperately want to keep out. Understanding when it succeeds and when it fails requires diving into the physics, and I promise to make this as painless as possible, because this is the difference between civilization continuing uninterrupted and transformers exploding across 3 continents. The interplanetary magnetic field, abbreviated IMF, pervades all of space between the planets. It originates from the sun's own magnetic field, carried outward by the solar wind, the continuous stream of charged particles our star breathes into the void. The IMF has 3 components. BX points toward or away from the sun, by points sideways, and B's points north or south. Of these 3, BZ's is the troublemaker, the variable that determines whether a CME's energy couples efficiently with Earth's magnetosphere or mostly slides off harmlessly. Earth's magnetic field points from south to north. When an incoming CME carries a magnetic field pointing in the same direction, north, the 2 fields are aligned. Magnetic fields of the same orientation repel. The CME's energy has difficulty penetrating Earth's magnetic defense. Storm effects remain moderate, but when the CME's field points south, opposite to Earth's field, something called magnetic reconnection occurs. field lines snap and reconnect in new configurations, creating portals through which solar wind energy floods into the magnetosphere. The shield doesn't just lower, it opens doorways. On January 19th, as the CME from active region 4341 slammed into Earth's magnetic field, instruments aboard satellites like NOAA's DSCOVR spacecraft measured the BZ component. The data showed periods of northward orientation during the storm's peak intensity. Not perfectly north, not consistently north, but enough to significantly reduce the coupling efficiency. If you want a number, geomagnetic storms with strongly southward BZ, say -20 or 30 nanoteslas, can drive KP indices to 8 or 9, the maximum on the scale. Saturday's storm reached KP 8, classified as G4 severe, but could have easily hit KP 9, classified as G5 extreme, with more southward BZ. That difference, that one step on the scale, represents billions of dollars in potential damage avoided. Here's the terrifying part. We cannot predict BZ orientation more than about 15 to 30 minutes in advance. When a CME leaves the sun, we can calculate its speed, estimate its arrival time, give or take 6 to 12 hours, and make educated guesses about its magnetic field strength. But the internal structure of the CME, the twists and coils and compressed layers within the magnetic cloud, that's chaos, literally. As in mathematical chaos theory, tiny changes in initial conditions propagate and amplify. The magnetic field rotates, interacts with other structures in the solar wind, gets stretched and compressed. By the time it reaches Earth, the orientation might be completely different from what it was when it left the sun. The DSCOVR spacecraft orbits at the L1 Lagrange point, a gravitationally stable position about 1.5 million kilometers sunward of Earth. It sits there specifically to give us early warning, measuring the solar wind in real time. When it detects a CME arrival, scientists have roughly 15 to 30 minutes before the same material hits Earth's magnetosphere. 15 to 30 minutes to decide whether to issue warnings to power grid operators, satellite companies, airlines, anyone who might be affected. 15 to 30 minutes to prepare for something that could, in the worst case, end modern technological civilization as we know it. This brings us to geomagnetically induced currents, or GICs. When Earth's magnetic field fluctuates rapidly during a geomagnetic storm, those fluctuations induce electrical currents in any long conductor. Power lines are very long conductors. The GICs flow through the grid, invisible parasites piggybacking on the transmission network. In moderate cases, they cause harmless voltage fluctuations. In severe cases, they saturate transformer cores, heating the metal, breaking down insulation, potentially destroying transformers that take months or years to replace and cost millions of dollars each. On March 13, 1989, a CME with strongly southward BZ component hit Earth. Within 90 seconds, the entire Quebec power grid collapsed. 6 million people lost electricity. It was March in Canada, still winter, temperatures below freezing. The blackout lasted 9 hours. Some areas remained dark for days. Imagine the same scenario, but instead of one regional grid, it's 20 grids across multiple countries. Instead of 9 hours, it's 9 months. That's the Carrington scenario. That's what strong southward BZ can do when it couples with a fast, dense CME. Saturday's storm, despite its impressive speed and particle flux, produced relatively modest GICs in most monitored power systems. Not zero, enough to concern engineers, but not enough to cause widespread failures. The magnetic orientation saved us, but it nearly didn't. There were periods during the storm when BZ dipped southward. Brief periods, not sustained, but enough to spike the KP index and light up auroras across lower latitudes than initially expected. If those southward periods had lasted longer, if the magnetic cloud had been twisted differently, we'd be telling a very different story right now. Scientists are working on better prediction methods. Machine learning models trained on decades of satellite data. Improved solar wind modeling. New spacecraft missions to observe the sun's poles and provide better three-dimensional data on CME structure. But fundamentally, we're still reading tea leaves. We're still hoping the dice roll in our favor. And the dice are about to roll again. As I'm recording this, the sun hasn't calmed down. If anything, the magnetic complexity in active region 4341 has increased. X-ray flux monitors show continued elevated activity. Other regions, not yet fully rotated into Earth view, are showing signs of instability. The probability of another major flare in the next 72 hours is high, and when that flare occurs, when the next CME races toward us, we'll have the same uncertainty, same 15-minute warning, same cosmic dice roll on magnetic orientation. But there's another angle to this story, something stranger, something that operates at the intersection of physics and coincidence. While the CME was battering Earth's magnetosphere, while scientists were monitoring BZ orientation and power grid operators were watching their instruments, something else was happening. Deep underground, along one of the most famous and feared fault lines on the planet, the Earth was moving. Not in the slow, steady creep of tectonic motion, but in sharp, violent jerks. Dozens of them. And the timing raises questions that make some scientists uncomfortable and others excited. Questions about whether the sun's fury and Earth's anger might be connected in ways we never imagined. Let me be clear right from the start. The scientific consensus is unequivocal. Solar storms do not cause earthquakes. The energy scales don't match. The physical mechanisms don't connect. The correlation is spurious. Every respectable seismologist and space physicist will tell you this, and they're probably right. Probably. But then why, on January 18th and 19th, as the S4 radiation storm peaked and the G4 geomagnetic conditions battered our magnetosphere, did the San Andreas fault experience one of the most intense earthquake swarms in recent memory? The San Andreas fault runs roughly 800 miles through California, a transform boundary where the Pacific plate grinds past the North American plate at about 2 inches per year. That slow motion accumulates stress. Eventually, the stress exceeds the friction holding the plates together, and they slip. Earthquakes. This is geology textbook material, driven by heat from Earth's interior. The slow convection of the mantle. Forces that have nothing to do with the sun or space weather or magnetic fields in the ionosphere. Nothing. Except during the January 18th to 19th period, seismometers recorded dozens of small to moderate earthquakes along the San Andreas system. Not tiny microseisms, detectable only by sensitive instruments, but legitimate quakes in the magnitude 3 to 4 range, enough to feel, enough to knock objects off shelves, enough to get reported by thousands of people on the USGS Did You Feel It website. The swarm was concentrated in segments that have been relatively quiet for months, and the timing, the precise temporal coincidence with the peak of the solar storm, is striking enough that it's being discussed in forums, on social media, in late-night conversations between geophysicists who would never put such speculation in a peer-reviewed paper. Correlation does not imply causation. This is drilled into every science student from their first statistics class. If ice cream sales and drowning deaths both increase in summer, that doesn't mean ice cream causes drowning. There's a hidden variable, warm weather, driving both. So what's the hidden variable here? Maybe there isn't one. Maybe this is pure coincidence, a random alignment of independent events that our pattern-seeking primate brains latch onto because we're wired to find meaning in chaos. But let's indulge the speculation for a moment. Let's ask the forbidden question. Could there possibly be any mechanism, no matter how tenuous, by which solar activity might influence tectonic behavior? The answer requires understanding how far the sun's influence actually reaches into Earth's various systems. Solar storms primarily affect the magnetosphere and ionosphere, the outer layers of Earth's atmosphere between roughly 60 and 1,000 kilometers altitude. The ionosphere is ionized, filled with free electrons and charged particles. When geomagnetic storms pump energy into this region, the ionosphere heats up, expands, becomes more conductive. Electric currents flow along magnetic field lines. The entire structure becomes a dynamic, turbulent mess of electromagnetic activity. This is well-documented physics. Some researchers, operating at the fringes of mainstream science, have proposed something called lithosphere-ionosphere coupling. The idea is that electromagnetic disturbances in the ionosphere could, through mechanisms that remain poorly defined, influence the stress state of rocks in Earth's crust. Perhaps through induced currents in conductive mineral layers. Perhaps through subtle changes in the electrical properties of fault zones, which are often more conductive than surrounding rock due to fluids and fractured material. Perhaps through mechanisms we haven't discovered yet because we haven't looked hard enough. The evidence for this is thin. Very thin. A few papers showing statistical correlations between geomagnetic storms and increased seismic activity, usually small earthquakes, usually with marginal significance levels that make most seismologists roll their eyes. The mechanism remains theoretical at best, non-existent at worst. If lithosphere-ionosphere coupling is real, the energy transfer would have to be extraordinarily efficient, amplifying tiny electromagnetic disturbances into mechanical stresses sufficient to trigger fault slip. That seems unlikely given what we know about rock mechanics and electromagnetic field propagation. And yet, there are historical curiosities. On September 2nd, 1859, during the Carrington Event, there are scattered reports in newspaper archives of unusual seismic activity. Nothing definitive, record-keeping was spotty, but enough to make you wonder. In November 1982, another major solar storm produced intense auroras and disrupted telegraph systems. Within the same 48-hour window, several moderate earthquakes were recorded in seismically active regions. Again, possibly coincidence. Again, possibly something else. The human mind is a pattern recognition machine run amok. We see faces in clouds, hear messages in static, find conspiracies in random data. We remember the hits and forget the misses. Confirmation bias is powerful. For every earthquake that occurs during a solar storm, dozens occur when the sun is quiet. For every solar storm, dozens happen without accompanying seismic activity. Cherry-picking examples proves nothing. But here's what keeps this idea alive, what prevents it from being completely dismissed. We don't fully understand earthquake triggering. We know the broad strokes, tectonic stress accumulation, eventual failure, aftershocks. But the precise timing of quakes, why they happen at one moment rather than another, that remains mysterious. Earthquakes can be triggered by external factors. We know this. The tidal forces from the moon and sun do influence seismic rates, though the effect is small. Reservoir filling from large dams can trigger quakes. Wastewater injection definitely triggers quakes. So the principle that external forces can nudge a fault system from stable to unstable is established. Could electromagnetic disturbances be another nudge? A tiny perturbation that, in a fault system already loaded with stress and ready to slip, provides just enough additional energy to push it over the edge? It sounds like pseudoscience. It sounds like something you'd read on a conspiracy theory website sandwiched between articles about chemtrails and lizard people. But science has a history of dismissing ideas as impossible, right up until someone proves they're not. I want to be absolutely clear. I am not claiming solar storms cause earthquakes. I am not suggesting you should prepare for a megaquake every time the sun hiccups. The mainstream scientific position is almost certainly correct. But I am suggesting that our understanding of how Earth's various systems interact, how energy flows between the sun, the magnetosphere, the ionosphere, the atmosphere, the oceans, and yes, even the crust is far from complete. We live on a planet embedded in a dynamic star system, and we've only been studying the connections seriously for about 70 years. A blink of an eye in geological time. The January earthquake swarm along the San Andreas will be studied. Seismologists will analyze the waveforms, map the epicenters, and calculate the stress changes. They will almost certainly conclude that the quakes were the result of normal tectonic processes, unrelated to the solar storm. And they're probably right. But every so often, probably will turn into possibly, and possibly will crack open into a whole new field of study. Maybe this is that moment? Probably not. Possibly. What we can say with certainty is that the solar storm didn't kill anyone. The earthquakes didn't kill anyone. This time. But the sun isn't finished, and neither is the San Andreas. Both are building towards something larger, something that will eventually arrive, regardless of whether they're connected. The only question is when, and whether we'll be ready. Because beyond the direct effects of magnetic storms and ground shaking, there are other impacts, subtler and stranger, that we're only beginning to recognize. The satellites went blind first. Not all of them, not permanently, but for hours during the peak of the radiation storm on January 19th, dozens of scientific and commercial satellites reported sensor anomalies. Star trackers, the devices that help satellites figure out their orientation by identifying patterns of stars, suddenly couldn't identify anything. The high-energy protons from the solar radiation storm were crashing through the detectors, creating false signals, phantom stars appearing and disappearing. One satellite operator told colleagues it was like trying to navigate while someone randomly punched you in the eyes. Vivid, accurate, terrifying. This is the hidden cost of space weather. The impacts that don't make headlines because they don't cause immediate catastrophe, but accumulate over time, degrading systems, shortening lifespans, adding up to billions of dollars in losses that get written off as expected operational costs. Every satellite has a radiation budget, a total dose of high-energy particles it can absorb before sensitive electronics start failing. Solar storms don't just damage satellites suddenly. They age them rapidly, stealing months or years of operational life in hours or days. During the S4 storm, airlines rerouted polar flights. The radiation dose at typical cruising altitudes increases near the poles where Earth's magnetic field funnels particles down. Flight attendants and pilots on those routes are considered radiation workers by some regulatory agencies, their annual exposure monitored like nuclear power plant employees. During an S4 event, the dose rates can spike 10 to 100 times normal. A single polar flight during the storm peak could deliver a radiation dose equivalent to several chest X-rays. Not immediately dangerous, but not something you want to repeat frequently. Pregnant flight crew are grounded during such events. Cancer risks, though small for any individual flight, add up over careers. Astronauts aboard the International Space Station retreated to more shielded sections of the station. The ISS orbits at about 400 kilometers altitude, low enough that Earth's magnetic field provides some protection, but high enough that during major solar storms, the radiation environment becomes genuinely hazardous. The 6 crew members currently on board could do nothing but wait, huddled in modules with better shielding, and hope the storm passed quickly. Future missions to the Moon or Mars won't have Earth's magnetosphere for protection. Astronauts will face the full fury of solar storms with only their spacecraft hull and maybe a water tank positioned strategically between them and the sun. It's a problem that space agencies know about, worry about, and don't have great solutions for. But the weirdest effects, the ones that border on science fiction, involve GPS. Most people think of GPS as straightforward. Satellites broadcast signals, your phone receives them, math happens, you get a position. Simple. Except the math requires incredibly precise timing, accurate to nanoseconds, and incredibly precise knowledge of the signal's path through the atmosphere. Geomagnetic storms scramble the ionosphere, creating density fluctuations that bend and delay GPS signals unpredictably. The result is positioning errors, sometimes small, a few meters, sometimes large, tens, or even hundreds of meters. Your phone might think you're on the wrong side of a bridge, or in the next town over. For most consumer applications, this is annoying, but not critical. For autonomous vehicles, precision agriculture, surveying, maritime navigation, aviation, it's potentially disastrous. Pilots relying on GPS-guided approaches to land in low visibility could find their positioning suddenly unreliable. Ships navigating narrow channels could drift off course. The technology we've built our modern infrastructure around has a hidden dependency on the sun behaving itself, and we noticed this dependency only after we were already committed. And then there are the biological whispers, the correlations so subtle and controversial that mentioning them risks credibility, but fascinating enough that they won't go away. Some researchers, typically operating outside mainstream medicine, have reported statistical associations between geomagnetic storms and human health effects. Increased hospital admissions for cardiovascular events, changes in mood and sleep patterns, migraine headaches, depression episodes. The proposed mechanism involves disruption of circadian rhythms or direct effects on the pineal gland and melatonin production. But the evidence is weak, studies are small and poorly controlled, and the effect sizes, if real, are tiny. Yet anecdotes persist. People swear they can feel geomagnetic storms, that they get headaches, or feel anxious when the KP index spikes. Skeptics, correctly, point out that humans are notoriously bad at assessing such correlations, that we remember the times we felt bad during a storm and forget the times we felt bad when the sun was quiet. Confirmation bias is powerful, but some migratory birds and sea turtles navigate using Earth's magnetic field. If geomagnetic disturbances can confuse a turtle's navigation, why couldn't they affect human biology in some subtle way? We have magnetite crystals in our brains, remnants of evolutionary history. Are they functional? Probably not, but probably isn't never. There are stories, unverified and probably apocryphal, of unusual animal behavior during major geomagnetic storms. Dogs howling for no apparent reason, flocks of birds circling in confusion, cattle becoming agitated. These stories date back centuries, mixed with aurora observations in historical records. Scientists dismiss them as folklore, and they're probably right. Probably. But the absence of evidence isn't evidence of absence, and the sun's influence on Earth's environment is so pervasive, so deeply woven into every system, that finding all the threads feels like an endless task. One area where the evidence is stronger involves the plasmasphere, a region of relatively cool, dense plasma correlating with Earth between the inner magnetosphere and ionosphere. During geomagnetic storms, chunks of the plasmasphere can get ripped away and ejected into space. This affects radio wave propagation, creates plasma irregularities that cause communication disruptions, and might influence how energy couples from the solar wind into the inner magnetosphere. We've only been studying the plasmasphere seriously since the 1960s. There are space missions planned to investigate it more thoroughly, satellites that will fly through it, measure its properties, watch how it responds to solar storms. What we'll discover remains unknown. That's the unifying theme here. Unknowns. We've built a technological civilization in the space of about 200 years, a civilization dependent on electricity, satellites, precise navigation, computer networks, all of it vulnerable to space weather in ways we're still mapping out. And we did this during a period, roughly 1970 to 2010, when the sun was unusually quiet. Solar cycles during that period were relatively weak. We got lucky. Now, cycle 25 is ramping up, possibly toward one of the stronger maxima in recent history, and we're discovering just how much of our infrastructure assumes the sun will stay calm. The January 19th storm was a test. A pop quiz we barely passed. But the sun isn't done testing us. It's barely started. And if we want to understand what might be coming, we need to look backward at the times when the sun stopped playing nice and showed us what it's really capable of. History isn't just the story of human civilization. It's also the story of what our star has done to us, repeatedly, and what it will almost certainly do again. Richard Carrington was 23 years old when he inherited his father's brewery. He promptly sold it and used the money to build a private observatory because some people know exactly what they want to do with their lives. On September 1st, 1859, shortly before noon, Carrington was projecting an image of the sun onto a screen in his darkened observatory, sketching the sunspots visible that day. This was standard astronomical practice, a safe way to observe the sun without burning your retinas. Then he saw something that shouldn't have been possible. Two brilliant, intensely bright spots appeared among the sunspots, so luminous that for a moment, Carrington thought something was wrong with his equipment, that perhaps a shaft of sunlight was leaking in and hitting his projection screen. But the spots moved, changing shape, sweeping across the sunspot group, lasting about 5 minutes before fading away. Carrington ran to find someone, anyone, to confirm he wasn't hallucinating. He found one person, another observer who caught the last moments of the event. Together they had witnessed the first observation of a solar flare, though the term wouldn't be coined for decades. 17 hours and 40 minutes later, the real show began. Auroras erupted across the globe, visible from the Arctic to the Caribbean, from Chile to Australia. Newspapers reported that people in the Rocky Mountains woke at 1 in the morning, convinced dawn had arrived, and began their daily routines. In Boston, a ship's captain recorded that he could read a newspaper by aurora light at 1:30 a.m. Telegraph operators across North America and Europe watched in horror as their equipment sparked and smoked. Some received electric shocks. Papers ignited. Messages could be sent with the batteries disconnected, powered entirely by the geomagnetically induced currents flowing through the wires. One operator in Boston disconnected his battery at 7 p.m. and continued sending and receiving messages for over 2 hours using only the aurora-driven currents. What had happened? We can reconstruct it now with modern understanding. Carrington's flare was likely X45 or stronger, perhaps the most powerful flare in modern history, though the classification system didn't exist then, and we're extrapolating from historical descriptions. The flare launched a coronal mass ejection of extraordinary size and speed, possibly 2,000 kilometers per second or faster. When it hit Earth, the magnetic field orientation was perfectly aligned for maximum energy coupling. The resulting geomagnetic storm was, as far as we can tell, the strongest in at least 500 years of recorded history. If the Carrington event happened tomorrow, what would occur? Studies have modeled this extensively, and the answers are sobering. The initial blast of high-energy particles would take out or severely damage a significant fraction of satellites in low Earth orbit. GPS would degrade or fail entirely. Communication satellites would go silent. The International Space Station's crew would face lethal radiation doses if they couldn't reach shielded areas quickly enough. That's day 0, the opening salvo. The CME itself arrives maybe 12 to 18 hours after the flare. Geomagnetically induced currents would flow through power grids across multiple continents. Transformers would begin failing, not all at once, but in cascades as each failure overloads neighboring transformers. Within hours, large sections of the power grid would be down. And here's the nightmare scenario. Large high-voltage transformers are custom-built, take months to manufacture, cost millions of dollars each, and aren't stockpiled in large numbers. Replacing them across an entire continent could take years. A 2012 study by the National Academy of Sciences estimated that a Carrington-class event today could cause $2 trillion in damage in the first year, with full recovery taking 4 to 10 years. 20 to 40 million people could be without power for months. Water systems fail after a few days when backup generators run out of fuel. Food distribution collapses. Hospitals struggle. The scenario looks less like a natural disaster and more like the collapse of industrial civilization across affected regions. And before you dismiss this as alarmist, remember, it already happened once. Why assume it can't happen again? March 13, 1989 provides a smaller scale preview. A CME with strongly southward magnetic field orientation slammed into Earth. The Quebec power grid, which serves 6 million people, collapsed in 90 seconds. Transformers at the James Bay hydroelectric facility saturated and shut down. Cascading failures ripped through the system. 6 million people lost power. It was March. It was cold. Some areas remained dark for days. The entire event was triggered by a storm weaker than Carrington by possibly an order of magnitude. 2003 gave us the Halloween storms, a series of violent solar eruptions including an X-28 flare, the second most powerful on record. Satellites were damaged. Airlines rerouted flights. Power grid operators in North America and Europe took emergency measures to prevent transformer damage. The Swedish ESA Smart 1 satellite suffered memory corruption. Mars missions reported electronic glitches. We got lucky again, because the most powerful CMEs missed Earth. One of them would have been devastating had it hit. May 10th and 11th, 2024 delivered the most powerful geomagnetic storm since 2003, possibly since 1989. Multiple CMEs erupted from a massive sunspot complex and arrived at Earth in close succession, a 1-2-3 punch that overwhelmed the magnetosphere. Auroras were visible from Mexico to southern England. Farmers in the Midwest United States reported GPS-guided tractors going haywire, driving in circles, unable to maintain position. Starlink satellites degraded. Power grid operators held their breath. And again, we got lucky. The magnetic orientation could have been worse. Then there's the one that got away. July 23, 2012. A massive CME erupted from the sun and tore through Earth's orbit at approximately 3,000 kilometers per second, one of the fastest CMEs ever recorded. It packed a magnetic field strength 4 times normal. If it had erupted 1 week earlier, when that region of the sun was facing Earth, it would have hit us. Some researchers estimate it would have been comparable to, or stronger than, the Carrington event. We never saw it coming because it happened on the far side of the sun. Pure cosmic luck. The difference between our current technological civilization and a multi-year recovery was 1 week of the sun's rotation. This is what keeps space weather scientists up at night. Not the events we can see coming and prepare for, but the recognition that major solar storms are not rare. They happen every few centuries at the Carrington scale. They happen every few decades at the Quebec or Halloween scale. The sun doesn't care about our infrastructure. It doesn't care that we've built a world dependent on electricity and satellites. It's going to do what it does, and sometimes what it does is terrifying. There are hints in historical records of other superstorms. In 1882, auroras appeared globally. Telegraph systems failed, and some astronomers reported exceptionally large sunspots and brilliant flares. The records are fragmentary, but the magnetic disturbance seems to have rivaled Carrington. In 1770, there's a peculiar gap in records, then mentions of brilliant auroras visible from the tropics. Were these Carrington-scale events that simply weren't documented because the technological infrastructure to feel their effects didn't exist yet? Ice cores tell another story. Certain isotopes, beryllium-10 and carbon-14, are produced when cosmic rays hit Earth's atmosphere. Solar storms suppress cosmic rays, creating dips in the isotope records. By drilling ice cores from Greenland and Antarctica, scientists can reconstruct solar activity, going back thousands of years. The data shows spikes suggesting Carrington-scale events, roughly once every 500 years. But there are larger spikes, events that might have been significantly more powerful than Carrington. We were just fortunate they occurred before we'd built a civilization vulnerable to them. The message from history is clear. The sun has done this before, and will do it again. The only questions are when and whether we'll be ready. Current space weather forecasting is primitive compared to meteorological forecasting. We can predict a hurricane's path 3 to 5 days in advance with reasonable accuracy. We can predict a CME's arrival time to within about 6 hours if we're lucky, and we can't predict its magnetic orientation at all until it's 30 minutes away. This is a problem. Various proposals exist to improve the situation. More satellites at different positions around the sun to give better views of CME structure. Better models incorporating machine learning and physics-based simulations. Hardening of critical infrastructure, though the costs are enormous. Stockpiling spare transformers, though political will for such long-term preparation is usually absent until after disaster strikes. We're in the awkward position of knowing a threat exists, understanding roughly how bad it could be, and doing less than we probably should to prepare for it. The January 19th storm has refocused attention. Congress members who barely knew what a CME was last week are now asking questions. Power grid operators are reviewing their storm protocols. Satellite companies are checking their redundancy systems. And the sun, indifferent to all this activity, continues preparing its next performance. Because this isn't over. We're not done. The curtain hasn't dropped. If anything, we're just reaching the end of the first act. The sunspots haven't gone away. Active region 4341, the source of Saturday's fury, is still visible on the solar disk, still magnetically complex, still crackling with energy. But it's not alone anymore. As the sun rotates, bringing new real estate into Earth view, other regions are appearing. Magnetograms, the maps that show magnetic field strength and complexity on the solar surface, look like topographic maps of mountain ranges. Each peak represents a potential eruption site, and right now there are several peaks. Solar flare forecasting is part science, part art, part educated guessing. Forecasters look at sunspot configuration, magnetic complexity metrics like the total unsigned magnetic flux, historical patterns, X-ray background levels. They feed this data into models, both physics-based and statistical. The models spit out probabilities. There's a 40% chance of an M-class flare in the next 24 hours. There's a 10% chance of an X-class flare. These numbers sound precise, scientific. They're really just sophisticated ways of saying maybe. The current forecast, as I'm recording this on January 21st, 2025, suggests a moderate to high probability of continued M-class flares and a meaningful chance of another X-class event in the next 72 hours. The regions currently visible have the magnetic configuration conducive to major eruptions. But forecasting gets complicated because we only see one side of the sun at a time. The far side, currently rotating into view over the next week or two, is a mystery. There could be massive active regions there, or nothing. We won't know until they appear over the limb. Missions like NASA's Stereo spacecraft used to help with this. Stereo A and Stereo B were positioned to give side views of the sun, effectively seeing what was coming before it rotated into Earth view. But Stereo B was lost in 2014. And Stereo A is now limited in its viewing geometry. We're partially blind again, dependent on Earth-based observations and near-Earth satellites that only see what the sun shows us directly. Let me walk you through some scenarios, purely speculative but grounded in physics and historical precedent. Scenario 1. Another X-class flare erupts from active region 4341 in the next 48 hours. It launches a CME, this one even faster than Saturday's, traveling at 1,300 kilometers per second. When it arrives, DSCO-VR measures the magnetic field and finds BZ is strongly southward, -25 nanoteslas, sustained for 12 hours. The resulting geomagnetic storm hits G5 extreme. Transformers fail across North America and Europe. Satellites drop offline. GPS becomes unusable for days. Economic losses exceed $100 billion. Recovery takes months. Scenario 2. Saturday's CME disturbed the magnetosphere, leaving it in a sensitive state, compressed and energized. Before it fully recovers, another CME arrives, smaller than Saturday's but still significant. The 1-2 punch, hitting a magnetosphere that hasn't recovered from the first blow, produces effects disproportionate to either CME individually. This is called a compound event, and we don't fully understand how they work. The magnetosphere might have a kind of memory, a relaxation timescale that makes consecutive hits more dangerous than either would be alone. Scenario 3. A series of moderate flares over the next week launches multiple small to medium CMEs. None individually would cause major problems, but they arrive in sequence, creating sustained but moderate geomagnetic storm conditions. This drags on for days, maybe a week. Satellite operators watch their radiation dose accumulate. Power grid operators stay on high alert, monitoring for unusual GIC levels. Aurora photographers have the time of their lives. The public, initially alarmed, gets bored and stops paying attention. Then, just as things seem to be calming down, a major CME hits the already stressed magnetosphere. Cascade effects ensue. None of these scenarios are guaranteed. All are possible. The probabilities are hard to pin down because we're dealing with a chaotic system observed from a single viewpoint with limited predictive capability. It's like trying to forecast tornado formation while only being allowed to look at weather maps from one city and only updated every 12 hours. You can make educated guesses, but you're going to miss things. There's an uncomfortable parallel here to the earthquake speculation from earlier. Both solar flares and earthquakes are examples of complex systems undergoing sudden transitions from one state to another. Both involve energy accumulation followed by rapid release. Both are extremely difficult to predict in detail, despite our understanding of the underlying physics. And both, in the January events, happened within hours of each other. Coincidence? Almost certainly. But it highlights how much of nature's timing remains opaque to us. The next 72 hours will tell us something. If another major flare occurs, if it launches a CME, if that CME hits Earth, we'll learn whether Saturday was a one-off or the beginning of a more sustained period of solar activity. We'll also get another roll of the magnetic dice, another chance to see whether nature favors us with benign BZ orientation or decides to give us a real test. And make no mistake, a real test is coming eventually. Maybe this week, maybe this year, maybe this decade, but it's coming. The statistics guarantee it. Carrington-class events happen. They're rare on human timescales, but not on solar timescales, not even on civilization timescales. We've been lucky. Our luck will run out. The only questions are when and whether we'll have done enough to prepare. Let's zoom out for a moment. Forget the technical details, the magnetograms, the B's components, the probability forecasts. Look at the situation from the widest possible perspective. We are biological organisms living on the surface of a rocky planet, third from a medium-sized star, located in the outer regions of an unremarkable galaxy. We evolved under a specific set of conditions, a magnetic field that shields us from cosmic radiation, an atmosphere that scatters blue light and gives us oxygen, a sun that's been relatively stable for billions of years. We adapted to these conditions so completely that we think of them as normal, as the default state of existence. Then, in the last blink of an eye in cosmic time, we built a technological civilization. We strung electrical wires across continents. We launched satellites into orbit. We created a global positioning system that relies on atomic clocks synchronized to nanoseconds. We built a world that assumes stability, that assumes the sun will continue doing what it's been doing, that assumes the ground won't shake too violently, that assumes the invisible magnetic field surrounding our planet will keep deflecting the worst of what space throws at us. And most of the time, these assumptions hold. The sun is stable on timescales of millions of years. Continental drift is slow. The magnetic field, though it flips polarity every few 100,000 years and weakens irregularly, generally protects us. Most of the time, the universe leaves us alone, but not always. Sometimes, the universe reminds us that we're not separate from it, that we're embedded in it, subject to its whims and its violence. The January 18th and 19th solar storm was such a reminder, a gentle reminder, as these things go, because we survived without major losses, but a reminder nonetheless. The sun is not a fixed yellow circle in the sky. It's a roiling ball of plasma held together by gravity, powered by nuclear fusion, threaded with magnetic fields that twist and snap and reconfigure in patterns we barely understand. It's capable of eruptions that dwarf anything in human experience. And we live, by necessity and by accident of cosmic geography, 150 million kilometers away from it, close enough to receive its life-giving light, close enough to be vulnerable to its occasional rage. The bee's orientation that saved us Saturday was luck. Not divine intervention, not human ingenuity, not superior forecasting, just luck. The magnetic field of the CME happened to be oriented in a way that reduced its impact. It could have been different. It will be different next time, or the time after that. And when it is, we'll find out how robust our infrastructure really is, how well our backup plans work, how quickly we can respond to large-scale technological failures. Some people find this terrifying. The recognition that our modern way of life depends on factors beyond our control. That a random fluctuation in solar magnetic fields could cascade into economic disaster. That we are, despite all our technology, still vulnerable to nature. I find it humbling and strangely beautiful because it means we're connected to the cosmos in immediate, tangible ways. The light from the sun that hit your face this morning left the solar surface 8 minutes and 20 seconds ago. The magnetic field protecting you from cosmic rays is generated by churning liquid iron 3,000 kilometers beneath your feet. The atoms in your body were forged in stellar cores billions of years ago. You are not separate from the universe. You are the universe examining itself. The earthquakes swarm along the San Andreas, whether related to the solar storm or pure coincidence, reminds us that Earth itself is dynamic, restless, full of energy and motion. The ground beneath your feet is not solid and stable. It's floating on a mantle that convects over millions of years, driven by heat from radioactive decay deep in the core. Continents drift. Mountains rise and erode. Faults slip. This has been happening for 4.5 billion years, long before humans existed, and it will continue long after we're gone. But we're here now. We're the first species on this planet, possibly the first in this corner of the galaxy, to understand these processes, to build instruments that can measure magnetic fields and seismic waves, to launch satellites that watch the sun and predict when it might lash out. We're the first to be vulnerable to space weather, because we're the first to build technology that space weather can disrupt. That's both a curse and a privilege. The technological and biological effects of solar storms are mixed. Satellite damage, communications disruptions, GPS errors, airline radiation exposure, these are documented and real. The biological effects on humans, the headaches, and mood changes, those are more speculative, based on weak correlations and anecdotal reports. They might be real. They might be placebo. They might be coincidence. The science isn't settled. The historical superstorms, Carrington, Quebec, Halloween, May 2024, these are documented and studied. The risks to modern infrastructure are real. The economic impact estimates are based on modeling and might be wrong, but the direction is clear. A major solar storm hitting Earth with the wrong magnetic orientation would cause significant, possibly catastrophic damage to modern technological systems. That's consensus among space weather experts. What happens next is genuinely unknown. The sun might calm down, it might ramp up. We might get another major CME this week, or we might not see another one for months. The probabilities favor continued activity as we approach solar maximum, but probabilities aren't certainties. Nature doesn't care about our forecasts. Here's what I want you to take away from this. The universe is not a backdrop to human activity. It's an active participant. The sun influences us daily in ways we rarely think about. Most of the time, it's benign. Sometimes it's not. We've built a world increasingly dependent on technologies vulnerable to space weather, and we've done this during a period when the sun was relatively quiet. Now the sun is waking up, and we're learning what that means. We're also learning about our limitations. We can't predict solar flares with precision. We can't predict the magnetic orientation of CMEs until they're nearly upon us. We can't say with certainty whether solar activity influences earthquakes, though we can say the mainstream view is skeptical. We can't guarantee that our infrastructure will survive the next major storm. There's a lot we don't know. Keep watching the sky. Keep learning about the universe we inhabit. Stay curious about the connections between systems, even speculative ones, because that's how science advances. But stay grounded in evidence, in physics, in the difference between what we know and what we wonder about. The sun will do what the sun does. Earth will do what Earth does. Our job is to observe, to understand, to prepare as best we can, and to marvel at the fact that we're conscious matter trying to comprehend the cosmos that created us. The next 72 hours might bring another storm. They might not. Either way, we're here, on this planet, under this star, living in interesting times. The Carrington Event happened 166 years ago. The next one is coming. Maybe soon, maybe not for centuries. But it's out there, somewhere in our future, waiting. And when it arrives, we'll find out if we learned anything from these warnings, these near misses, these cosmic reminders that we are, despite all our technology and understanding, still very small creatures in a very large universe that doesn't care whether we survive. Stay curious, stay informed, and maybe, just maybe, keep one eye on the sun.